how do you actually stop something that's moving at 25,000 miles per hour? That's the speed you're traveling when you come back from the moon. And you need to go from that speed to zero, preferably in one piece. There's no single answer to that question. The concept goes back over 100 years. Robert Goddard was thinking about it as early as 1920. But for the past 7 decades, engineers have been building real solutions. At least half a dozen completely different approaches, each one involving trade-offs, failures, and some genuinely surprising engineering. We already talked about the Artemis heat shield in previous videos, but that heat shield is just one answer. When a spacecraft re-enters the atmosphere at orbital speed, it's carrying an enormous amount of kinetic energy. Now you might think, why not just fire your rockets in the opposite direction and slow down? In theory, that works. In practice, you'd need almost as much fuel as it took to get you up there in the first place. And fuel is heavy, which means you need more fuel to carry that fuel. It's a vicious cycle that rocket engineers call the tyranny of the rocket equation. So instead, we use the atmosphere. The atmosphere is your brake pedal. When you hit it at hypersonic speed, it does an incredible job of slowing you down. The problem is that all that kinetic energy has to go somewhere, and it goes into heat. And here's the misconception: that heat is not mainly caused by friction. It's caused by compression. The spacecraft is moving so fast that the air in front of it can't get out of the way. It gets compressed so violently that it heats up to thousands of degrees. It actually becomes plasma. A superheated shock wave forms in front of the vehicle. Now, this is where one of the greatest counterintuitive discoveries in aerospace history comes in. In the early 1950s, 2 engineers at NACA, that's the predecessor to NASA, named Harvey Allen and Alfred Eggers were working on the re-entry problem. Everyone assumed that a sleek, pointed shape would be best for surviving re-entry. That's what you'd think, right? Cut through the air like a knife. Allen and Eggers proved the opposite. They showed that a blunt shape, a rounded, stubby shape, actually survives re-entry far better than a pointed one. And the reason is elegant. A blunt body pushes that superheated shock wave forward, away from the vehicle. The compressed air forms a cushion. Most of the extreme heat stays in the shocked gas and flows around the vehicle rather than into it. That discovery was classified as a military secret. It wasn't published until 1958, but it's the reason every crew capsule ever built, from Mercury to Gemini to Apollo to Soyuz to Orion, has that same blunt, rounded shape. It's all because of Allen and Eggers. So with that in mind, let's look at how we actually deal with the heat that does reach the vehicle. The oldest and most proven approach is the ablative heat shield, and the concept is beautifully simple. You build a shield out of material that's designed to sacrifice itself. As the spacecraft re-enters, the outer layer chars, melts, and vaporizes, carrying heat away as it goes. But underneath that charring surface, something else is happening. The inner layers decompose chemically, producing gases that filter outward through the porous char. Those gases create a thin boundary layer that actually pushes the superheated plasma away from the surface. The Apollo heat shield used a material called AV coat, packed into a fiberglass honeycomb, more than 300,000 individual cells filled by hand. It worked perfectly on every mission. On the robotic side, there's Pika, phenolic impregnated carbon ablative, which flew on the Stardust probe at the fastest re-entry speed ever recorded, and later on, Curiosity's Mars landing and SpaceX's Dragon capsule. These materials have long track records, but here's the thing about proven materials: they can still surprise you. When NASA built the Orion heat shield for Artemis, they went back to AV coat. Same name, same concept, but the original hadn't been manufactured in decades. Some ingredients were no longer available. Some of the know-how had been lost. NASA spent over $25 million and 5 years recreating it, and the version they ended up with behaved differently than the Apollo original in ways nobody fully anticipated. I covered the full story in my previous video: what went wrong on Artemis 1, what NASA found during the investigation, and why they decided to fly Artemis 2 anyway with a modified re-entry trajectory. I'll link that in the description if you want the complete breakdown. What I can tell you today is that it eventually worked. NASA says Artemis 2 landing data, including heat shield performance, will shape the Artemis 3 timeline. Ablative shields work, but they're single-use. Every time you fly, you need a new one. So what if you could build a thermal protection system that survives re-entry and can be used again? That was the philosophy behind the Space Shuttle's thermal tiles. Instead of burning away, these tiles insulate. They absorb the heat, re-radiate it, and come back ready to fly again. The material itself doesn't change, it just manages the energy. The shuttle's thermal protection system was an engineering marvel. Roughly 24,000 individual tiles made from ultra-pure silica fibers, essentially sand, processed into a material that was 94% air. They were astonishingly good insulators. But they were also extremely fragile. You could crumble one in your fingers. And here's what made the shuttle system truly daunting. Nearly every one of those 24,000 tiles was unique. Each one was individually shaped to fit its specific position on the orbiter. They couldn't be mass-produced. And between flights, they had to be individually inspected and often replaced. It was one of the major reasons the shuttle never achieved the rapid turnaround times NASA had originally hoped for. The vulnerability of this system was demonstrated in the most tragic way possible in 2003. During the launch of Columbia's final mission, a piece of insulating foam broke off the external tank and struck the reinforced carbon composite panels on the leading edge of the left wing. During re-entry 16 days later, superheated plasma penetrated through that breach, destroyed the wing's internal structure, and Columbia broke apart over the southern United States. All 7 crew members were lost. Columbia is a reminder that thermal protection isn't just about materials science, it's about margins. When the protection fails, there is no backup. There is no redundancy for the heat shield. Today, SpaceX is taking a very different approach with Starship. Instead of 24,000 unique tiles, Starship uses mass-produced hexagonal tiles designed for rapid replacement rather than obsessive individual maintenance. If one is damaged, you pull it off and snap a new one on. It's the same basic principle: ceramic insulation rather than ablation, but with a completely different engineering philosophy behind it. Now, tiles and ablatives both rely on the same fundamental idea. Let the atmosphere do the work. Use aerodynamic drag to slow down and manage the heat that comes with it. But what if there's no atmosphere to work with? If there's no atmosphere, or not enough of one, you're left with the brute force option. Point your engines in the direction you're traveling and fire them. Retropropulsion. This is the only way to land on the moon. There's no air, no drag, no heat shield in the world that can help you. Every single bit of deceleration has to come from the engine. That's why the Apollo lunar module looked the way it did. Spindly, fragile, almost skeletal. Every unnecessary gram of structure was a gram less of fuel, and you needed every drop. The descent engine on the lunar module burned for about 12 minutes to bring the spacecraft from orbital speed down to a gentle touchdown. 12 minutes of controlled thrust with no margin for error. On Earth, retropropulsion has become routine, at least for SpaceX. The Falcon 9 first stage performs a supersonic retropropulsion burn on every return, firing 3 of its 9 Merlin engines into the oncoming supersonic airstream to slow down for landing. They've done this hundreds of times now. But here's a story that most people don't know. In September 2013, SpaceX performed the very first supersonic retropropulsion maneuver on a Falcon 9. NASA noticed. Not because they were interested in landing rockets on Earth, they were interested in landing things on Mars. In 2014, NASA and SpaceX formed a public-private partnership specifically to study Falcon 9 re-entry data. NASA flew WB-57 high-altitude research aircraft equipped with infrared cameras to track Falcon 9 boosters as they descended through the atmosphere. They were particularly interested in the altitude range between about 40 and 70 kilometers, because at that altitude and speed, the Falcon 9 first stage experiences conditions remarkably similar to what a spacecraft would face entering the Martian atmosphere. NASA was essentially using SpaceX's commercial rocket landings as free Mars entry research data. And based on that work, NASA concluded that the core challenge of supersonic retropropulsion for Mars isn't really a technology problem anymore. It's a systems engineering problem. The question is how to integrate it into a Mars flight system. But retropropulsion has a fundamental limitation, and it goes back to the tyranny of the rocket equation. Fuel has mass. More fuel means more mass to decelerate, which means you need more fuel. This is why atmospheric braking is always preferred when an atmosphere exists. It's essentially free deceleration. And that's what makes Mars such an engineering nightmare. Mars has an atmosphere, but it's less than 1% the density of Earth's. Thick enough to create serious heating during entry, thin enough that it can't slow you down nearly enough to land safely. Right now, using current technology, NASA can land about 1 metric ton on the Martian surface. That's a Perseverance-size rover. Landing humans and their equipment on Mars will require 20 metric tons or more. And that brings us to what I think is the most exciting technology in this entire video. Here's something I love. After I posted a video about the Artemis heat shield, someone in the comments suggested something like, "What about a partially unfolded umbrella made of heat-resistant material?" That's a great intuition, because NASA has been working on exactly that concept for over a decade. And the idea is simple but powerful. Traditional heat shields are limited by the size of the rocket fairing they have to fit inside. The Orion heat shield is 5 meters across, about 16.5 feet, and that's about as large as you can practically build a rigid shield and fit it inside a rocket. But what if you could make your heat shield much bigger than your rocket? Pack an inflatable structure inside the fairing, launch it, then inflate it in space to a much larger diameter before re-entry. More surface area means more drag. More drag means deceleration starts higher in the atmosphere, where the air is thinner and gentler. You spread the heating load over a larger area, and you start slowing down earlier. In November 2022, NASA proved this works. The low Earth orbit flight test of an inflatable decelerator, LOFTID, launched as a secondary payload on a United Launch Alliance Atlas V rocket. After the primary satellite separated, LOFTID inflated its aeroshell to 6 meters, about 20 feet, across. At the time, it became the largest blunt body ever to re-enter Earth's atmosphere. It re-entered at more than 18,000 miles per hour. Temperatures on the heat shield reached nearly 2,700 degrees Fahrenheit. And it slowed to under 80 miles per hour before deploying parachutes and splashing down in the Pacific Ocean, just 8 miles from the recovery ship. NASA's post-flight assessment? They called the performance just flawless. The construction is fascinating. The inflatable structure is made of concentric rings, think of nested inner tubes, woven from a synthetic polymer that's 10 times stronger than steel by weight. Those rings are coated in a high-temperature silicone adhesive, which gives the whole structure that distinctive orange color you see in the photos. Covering the inflatable structure is a flexible thermal protection system with 4 layers. The outermost layer is a woven ceramic fabric, silicon carbide, made into fibers so fine they can be spun into yarn and woven on the same industrial looms used to make denim. Under that are 2 types of flexible insulation, and finally, a gas barrier to keep the structure sealed. LOFTID was the proof of concept. What comes next is where it gets really exciting. NASA has partnered with United Launch Alliance under the Tipping Point program to develop the next generation, a 12-meter HIAD, twice the diameter of LOFTID, designed to recover Vulcan rocket engines from orbit for reuse. But the real prize is Mars. NASA is developing 16 to 20 meter versions that could land 20 to 40 metric tons on the Martian surface. That's the difference between landing a rover and landing a habitat, between sending robots and sending people. It doesn't solve everything. You'd still likely need supersonic retropropulsion for the final descent, but it solves the first and most critical piece of the puzzle: getting from interplanetary speed to something a rocket engine can handle. Now, every method we've talked about so far has one thing in common. None of them can get you all the way to a safe landing speed on their own. At some point, you need that final step. And more often than not, that final step is parachutes. Parachutes can only deploy at subsonic speeds, below about 700 miles per hour. So they're never the first line of defense. They're the closer, the last act. Orion's parachute system is a good example of how complex that last act actually is. It uses 11 parachutes in total, deployed in a carefully choreographed sequence. First, 3 forward bay cover parachutes pull away the capsule's forward heat shield cover. Then 2 drogue chutes, each 23 feet across, deploy to stabilize and begin slowing the capsule. Then 3 small pilot chutes pull out the 3 main parachutes. Each main chute is 116 feet in diameter and weighs over 300 pounds. Together, they slow Orion from about 325 miles per hour down to roughly 17 miles per hour for splashdown. All of that, 11 chutes, a precise sequence, massive loads on the suspension lines, has to work every single time. Even the materials have been refined through testing. The suspension lines were originally designed with steel cables. Testing showed that a Kevlar-nylon hybrid worked better, so they switched. Parachutes are ancient technology. The concept goes back centuries, but getting them right for spaceflight, the materials, the sequencing, the redundancy, the deployment dynamics, is anything but simple. It's precision engineering applied to fabric and rope. So, how do you stop something moving at 25,000 miles per hour? The honest answer is, it depends entirely on where you're going. If you're coming home to Earth from the Moon, like the Artemis crew, you hit the atmosphere with an ablative heat shield. Let it char and burn and carry the heat away, and then deploy parachutes for the final descent. The atmosphere does most of the heavy lifting. If you're landing on the Moon, no atmosphere at all, it's pure retropropulsion. Engines burning all the way down. Every pound of fuel counted, every second of burn time critical. And if you're going to Mars, that's the hardest problem of all. Mars gives you just enough atmosphere to create serious heating, but not nearly enough to stop you. The answer will almost certainly be some combination of everything we've talked about today. Potentially an inflatable heat shield to slow down high in the thin atmosphere, then rocket engines taking over to bring you the rest of the way to the surface. Multiple technologies working in sequence, each one picking up where the last one left off. We're still inventing new ways to solve this problem. LOFTID flew just a few years ago. Falcon 9 re-entry data is feeding into Mars landing research right now. And all of it stands on a discovery made 70 years ago, that the best way to survive re-entry is, counterintuitively, to hit the atmosphere with the bluntest shape you can. The engineering only gets more interesting from here. If you want to come along for it, hit subscribe.